Hybrid machine learning is the combination of physics-based information along with empirical regression methods that are typical in machine learning. So we're adding some additional physics-based information to help with the prediction and extrapolation. We have a case study here on thermophysical properties. I'd like to go through this with you to demonstrate some of the potential power of this approach simply by adding things like constraints to the parameter weights. Now, there are many different types of hybrid machine learning methods that have been proposed, and let me just review some of those, some of the most popular methods for combining physics-based and machine learned models. We often think of those as maybe two separate approaches. You can either take a physics-based approach or a machine learned approach, but we're starting to see more and more of this combination of the two. So let me go into some of these. We have, for example, a physics-based information where somebody knows something about a process and they simulate that over and over to generate sample data. And then they perform machine learning on the input to output relationship of that data to basically learn the model, so you don't need to necessarily use the physics-based simulator anymore. Okay, the other way that we can use data and physics-based simulators is to potentially have this data and then we adjust some of the parameter weights in the physics-based model. So we're informing the physics-based approach. It's not purely theoretical at this point. We're using data to update some of those parameters. And then another way that many have proposed to do this is to take a physics-based approach and a machine-learned approach and subtract the difference between those two. And then you get a residual amount. And then you use that with machine learning, another potential machine learned method to be able to get the residual and do another machine learning model. So this can be either a physics-based model, and that can just be data, or it could be a machine learned method. You get a residual and then you use further machine learning to try to find any kind of additional correlation that you can use to improve the prediction. Okay, and one of the things that is also a potential is just to combine those. Okay, so you don't have to necessarily separate them into a physics-based approach and a machine learned approach. What if we started developing tools where you can seamlessly add constraints to machine learned models or other physics-based information? So let's just go through a couple hypothetical situations. Let's say you have a deep learning neural network here, multiple hidden layers, and you do something like add constraints, like all of the weights of that first row, okay, that first layer need to be greater than 0, for example. Or let's say you have some data like you see over here, where you see one cycle of something that should have a periodic conditions, and maybe you add, instead of the standard rectified linear units or hyperbolic tangent functions, you add, let me get hyperbolic tangent, or maybe you have sigmoid functions. Okay, maybe you add something new here, like a cosine function, instead of one of these other standard layers, and then you get predictions that extrapolate better outside of the training regime. And so there's some examples that are on the course website that show this approach on how to include physics-based information into these machine learned methods. And one of the reasons why I'm excited in particular about this case study is because it does a good job demonstrating the power of this approach with thermophysical properties. Now, if we take a TensorFlow Keras method and train with 1,000 epochs, you can see an example of overfitting here, where we did very good on the training data, but you can see the worst performance on the test set. Now, if you just limit the number of iterations or epochs, you can see there's more of a balance here. This is reduced, but this one doesn't have as high of a mean absolute error. Now, just replicated those with Gecko, and then also added a constraint. So we said that that very first layer has to be greater than 0, as we showed up here. And one of the interesting things that happened here is that we saw the best validation. Now, it's not by a lot, but we saw that there was the worst training, and this might seem like, hey, we don't necessarily want to use that because it didn't do so well on the training. But when we come down to the validation, where we give it new data points that have never been explored before, it had the best performance. And so by adding these constraints, in this case, that the group contribution has to be positive for Parachor predictions of surface tension. And we'll get into that a little bit more on what that is. But basically, we knew something about the regression, and we were able to impose that constraint and be able to improve the validation. So the performance on data that we didn't use for training. Okay, so let's go to the course website. I'm just going to direct you to the Google Colab. You can either solve this in Google Colab, or you can also use the Jupyter Notebook that's right here. Just go ahead and select this link. Either one that you'd like to use is fine. And then either save link as and go ahead and download that Jupyter Notebook to your desktop, or go ahead and do it through the Google Colab. So a little bit of background is we have some Parachor values that are a group contribution method to predict thermophysical properties such as surface tension or thermal conductivity. This Parachor value predicts, basically you have this value P that takes as well the difference between the liquid density and the vapor density times the Parachor to the 4th power, and that's an approximation of your surface tension. And so we have some data here. Here's some thermophysical property data, and it was reported in another publication. But what we have here is basically each of these chemicals here, like N-butane, and then here we have the different groups. Okay, so you have the number of each of those groups, and we're going to try to use that to be able to predict the surface tension, or in this case, let's see, we got the Parachor value here, which then will relate to the surface tension. Okay, so let's just see how we're going to do with this data. Okay, so we have, we're going to develop a prediction of the Parachor from the chemical compound data set. We'll report like a correlation coefficient R squared, or you can also do a mean absolute error or mean squared error, for example. We're going to randomly select values that split the data into 80% and 20%, and then we're going to add this constraint. Okay, so we'll enforce a positive Parachor contribution for each group, and then we'll discuss the performance on each of the training and test sets. Okay, so let's go ahead and get into the Jupyter Notebook. I'm going to show you a few examples of how to do this. You can't necessarily use some of these packages just in the generic ways that you've seen over and over again, unconstrained. We've got to do things just a little bit differently to be able to add constraints and be able to and solve those with the constraints. Okay, so let's just do a linear regression example first. All right, I'm just going to do this with Gecko, many other packages that you can use for linear regression, generate some sample data, and then Gecko model. I'm going to create my unknown parameters, A and B, which is going to be the slope and the intercept. So just a one-dimensional linear regression. I have some variables and parameters, the y predicted, y measured, and x measured values. And then I have my equation. And I'm going to try to minimize the difference between the predicted and the measured values squared. I'll solve that. And then let's go ahead and print just the slope and the intercept. Now I'm going to add a constraint. In this case, the slope has to be greater than or equal to 0. Maybe I have some kind of a understanding of the system. I know that this constraint should be there. Now I'll solve it again, and then let's just go ahead and compare the two with our plot. So I'll solve this one, and you can see initially the data, it's lying in this region here. You do see an unconstrained result, and then the constrained result as well, where it's greater than or equal to 0. So you can see that the prediction got worse, and it's as expected. The constraint is that it has to be greater than or equal to 0, and so it said that the slope had to be equal to 0. So this is just an example where the training is you can see it's gonna get worse with constraints as expected. Now let's predict thermophysical properties. All right, so I'm gonna use this URL right here with the data, and then what I'm gonna do now is go ahead and just do linear regression without constraints. Okay, so here's linear regression. I'm gonna read the CSV file. There's my inputs. The last 40 are the Parachor group contributions. I have the training and validation, and then we also have the measured output as well. Okay, and this is just going to be the Parachor value, and then we have linear regression as well. This is going to be just using linear regression just with NumPy and doing the calculations with the matrices. And then I'll solve for the slope, and there's my predicted output. I'll get my mean absolute error and then create a parity plot. So this helps me see the difference between the measured and the predicted values. And here I can see I have a linear training set and a linear validation set. And there I can see I've got good agreement. Here's one value right here that's a little bit of an outlier. Didn't do as well on that one. All right, so let's keep going. We have a neural network deep learning without constraints in Keras and TensorFlow. So here I have, this first one, I'm going to just load the packages. I'll import the data like I just did with linear regression. I'll get my input as I just did with linear regression as well. There's my Parachor value. And then let's just go ahead and scale the data. For neural networks, you need to scale it preferably 0 to 1, or you can also do a standard scaler with a mean 0 and standard deviation 1. And then we're going to scale the training and test set data. Okay, we'll train the model. I'm going through this a little bit fast because we've seen this before in other exercises. I'm just going to create a sequential model with dense layers with linear hyperbolic tangent and 2 linear layer outputs and the atom optimizer. And then I'm going to load the training data and train the model with 200 iterations or epochs. Okay, and then I'll test the model as well. We'll look at how it performs on the 20% of the data that we didn't use for training. All right, now here's some predictions also outside the training region. I'll unscale for plotting and then calculate some metrics for sum of absolute error. All right, let's go ahead and train this. Here's our thermophysical properties, and it's working. It just finished. Okay, so here you can see the training and the validation. You see the mean squared error. And you can see it as well, just like the linear regression, there's this one point here that didn't do as good on the regression results. So let's do this with Gecko as well. The Gecko has a deep learning library in it. Let me go to Gecko documentation. You have a deep learning library. This was the brain module within Gecko. And so to create a neural network with the different layers, you can see just an example here of how to create those different layers with linear, hyperbolic tangent, or others. And just a few more examples just with training neural networks. But we're not going to use this simplified approach right here in this library to learn and to predict. we're going to code it ourselves because we need to get down into these layers to add the constraint. So I'm going to import gecko. Matplotlib will read the data in. Let's get our layers and the sizes. Okay, I have an input, scale the data. There's our output, and we'll also scale those values as well. And we'll also get the unscaled and scaled values. I'll initialize gecko for the training and test models. And there's our model, train, and test. We will have the parameters, get our first layer. Now this is a little bit complicated, but basically we're just creating this neural network from scratch. And there you can see a hyperbolic tangent layer. Okay, if I wanted to add, for example, a cosine layer here, I could do something like that. There's cosine instead. But let's just keep going with these additional layers. Okay, there's layer 3, and then there's my output layer. So there's a lot of summations and just iterating through these to do all the calculations and add the equations. Gecko will then compile and provide automatic differentiation and a solver to solve it. Okay, we'll fit the parameter weights. I'm going to just put in some default values here and then tell that we need to turn those parameters on. Basically, we want to estimate them with our regression. Okay, if we wanted to add a constraint, we could uncomment this line here to add a lower bound to weight 1. We're going to do that later. Now let's do this for the second layer and the third layer. We're just going to turn on those parameters and then solve it. Okay, then we want to get the test sample points. Do something similar, just load in the values from the training set for all 3 of those. Okay, and then let me just come down here and add our input. We'll go ahead and solve it, and we'll unscale the output and then create our mean absolute error. Okay, let's create a parity plot as well. Okay, and let's see the performance on this parity plot. All right, so here are the results. We had our mean absolute error for training and validation. And here you can see this outlier. Okay, even without the constraints, it's not as bad on this one, but it's still not very good. Okay, this is a log plot, and so you can see how well it's predicting. All right, let's go ahead and just print the neural network weights now. We have some sample points. Here's our test. Okay, and if we print these out, we can see that we had some negative weights here. It means that it predicted that we had some negative contributions to the Parachor value. Basically, if you add that group in the chemical compound, it's going to have a lower Parachor value. And an idea is to say, well, let's just say that every group, when you add something to a compound, it's always going to have a positive contribution. And so let's just test that. Let's see what's going to happen if we enforce a constraint here that it always has to be positive, that we can't have negative values here. So maybe that's some kind of a knowledge that we can impose on the problem to help us improve the performance on data that we have not trained on. All right, you can see some other negative values here for the other weights, but I'm just going to leave those alone. I'm just going to enforce positive constraints just here on the W1 values. Okay, and so let's go ahead and you can either copy this or you can just come up here and uncomment this to add the constraint. Okay, so I'm just going to uncomment that to add the constraint. And then let's just see how it does in predicting for this data. Okay, just finished, and you can see the predictions now. You can see this particular outlier right here, this red dot, that before was always an outlier for all of the regressions. It's more in line with this 45-degree, basically along the predicted measured trend, and the black line would be absolutely perfect. So you can see that although it may have done just a little bit worse here on some of the other data sets, you can see the validation, it did better on the validation. So we've improved the fitting by adding that constraint to the problem. All right, so if I print out the neural network weights now, you can see that some of them are going to be 0 values. And that kind of surprised me as well. It's doing much better, but it said that certain groups have no contribution to the Parachor. And maybe we even need to add a positivity constraint like 0.01 or some other type of constraint to say that everything needs to have at least a small positive contribution. But the other ones can still be negative. Okay, so overall, we see that with this, we're going to see, worse training, but potentially the best validation. And so this thermophysical properties case study demonstrates the potential of using constraints or physics-based information in the regression to be able to improve the predictions. So I hope you've enjoyed this. We'll have other machine learning content here on the course website. We have a number of other case studies here that you can see that are grouped by regression, classification, time series, computer vision. We'll add some audio ones later. And there's more information on regression here with different methods. And in this one, we covered linear regression and then a neural network regressor, but there are others as well where you can potentially impose constraints or physics-based information with that. Okay, I hope you've enjoyed this, and check back again later for additional content. I hope you enjoy the Machine Learning for Engineers course.